Go.
A book is pushed at a constant velocity across the floor and then the pushing stops. The book travels a distance after it stops being pushed.
One last time. Thank you.
A book is pushed at a constant velocity across the floor and then the pushing stops. The book travels a distance after it stops.
Okay. So everybody, it will take you like a couple times reading the sentence, figuring out what's going on. The hardest thing for me with energy is to figure out the moments in time that are most useful. Now, I've learned from periods 4 and 5, the moments in time you want to think about it depends on your storage bins, really. Your storage bins are what? What are the 3? Okay, let's just talk elastic. If I have a rubber band and I stretch it, what's the most interesting moment in time? It's when the stretch is what? When the stretch is what? Maximum, yes. Because then you have the maximum amount of energy stored in elastic if the rubber band is part of your system. Go.
When you say maximum energy, isn't that just like maximum potential energy?
Maximum elastic potential energy?
Oh, wow.
Sure, that's right. And your system would have to have a spring, or your system would have to be made of rubber, or your system would have to have a trampoline or a bungee cord or a spring or something that's elastic, right? In order to store elastic energy. Now, another interesting, yeah, go.
Does that mean a rope?
Ropes will be absolutely clear when there's elastic energy. We'll say bungee cord. So rope, no. Wire, no. Bungee cord, yes. Rubber band, yes. Spring, yes. You guys good?
Yeah.
So we'll try to be absolutely clear there.
Wait, you said that elastic energy can be stored in anything.
Okay, technically you're right. In practice, we don't talk about the elastic energy stored in the desk that we stand on. We don't usually talk about that. We could though, and it's not wrong. There is elastic energy stored in the molecules of many different materials. But are we going to get that technical on you? No. You guys good? Okay. Huh? Well, you can be an engineer and study you can study constants that depend on the type of material that are fundamentally just telling you how elastic the material is. And that would be something more related if you're an engineer. Cool? All right. So in terms of kinetic energy, what moments in time are most useful?
When it's in motion.
Minimum and maximum speed, right?
Yes.
And in terms of energy stored in a gravity field, what moments in time are most interesting? Highest and lowest. Heights. Good. All right.
But what did it say about height being like 0 and not 0? You can make it 0 when you want, right?
We'll talk about that.
Okay.
We'll totally talk about that. Right now, looking at this problem, is there any change in height?
Yeah.
Is there any elastic material?
Yeah.
So right away, that takes care of 2 of your energy bands. So in the beginning, you are so not worried about elastic, or what's the other one you're not worried about here?
Gravitation.
Okay, so these are just not even in here. We don't even need them. Okay. In fact, later maybe you won't even write them. But for now, you should write all of them. You should write all the possible energy bands. Yeah. Now, a book is pushed at a constant velocity across the floor. What do you think your first moment in time is going to be?
When the velocity is. Actually, no, but if you push it, it's not going to be a 0.
I like your thought. So if you wanted your velocity to be 0, this would be 0, and that's fine. That would be true. Your velocity would be 0. At the moment, this is a beautiful hand. Appreciate the beautiful drawing of my hand. Just kidding.
It's been like 7 fingers.
That's 5.
It is?
Yes.
No, it's 6.
They're just not all the same length.
It's like.
Okay.
That's true.
Okay, so in my case, since I'm such a good artist, I should label my things so that you know what they are. That's a book. I think you figured that out. That's a hand. Yes?
For these problems, we don't take.
Can't hear you. Try again.
For these problems, we don't take height into account.
Well, in this particular problem, is there a height change? So, e.g., essentially whatever e.g. is in the beginning, it is in the end, so we don't care. An accountant is only worried here about where is the energy stored and how is it transferring from accounts. Good?
So we don't even write
Not necessary, because there's no height change. Now, what would you want your system to be? Anything else?
gravitation.
Okay, so book and gravity field?
No.
Why is the gravity field not necessary here? It just makes your problem more complicated when it doesn't need to be. You could. I'm going to leave the hand out of my system, and here's why. You haven't seen this yet. You had no way of knowing this yet. But how do you think you're going to add energy to a system? System here being book. How could you add energy to the book?
I'm gonna say.
Now, notice something. On the very simplest case, book moves horizontally, right? Which way is it being pushed? Same direction? So, if the force on the book and its displacement are in the same exact direction, guess what? You think we're adding energy to our system? You think we're taking away from our system? You guys good? We have a name for this. So this is energy transferring in, which you're the first time you've seen before. We call this work or working, whatever you prefer. So work is really just energy transferring into or out of a system by means of a force. You guys cool? So there's a force on our system. Our system moves in the direction the force is applied. Energy is added to our system. Are you guys good? How many blocks do you want? How many blocks do you want to be added? 4?
Is this arbitrary?
No. It has to be a number between 0 and infinity. I thought that was fun. Okay. So, then what? Next interesting moment in time is when?
Yeah, let's go.
Good. So it's at the moment exactly when the hand lets go. So the hand is still there, but whoever's beautiful hand this is has just let go. I should probably write that because you won't actually know from my picture. So hand
It's like this.
just stopped pushing. Everybody good there? Everybody cool?
There we go.
And what can you tell me about the velocity at that moment in time? Is the velocity maximum?
Yes.
These types of things are very important. And when we talk about energy, this idea is very important. So now, copy our bins over. I got E elastic, which of course I don't have to worry about. I got EG, which of course I don't have to worry about. And I got EK. And since the velocity is maximum, I suppose I should highlight that. I'll put some little lines in to show that it's moving. It's moving fast, okay? Relative to not moving, right? 4 blocks go in. Where do they go? Do they all make it to EK?
No, I lost the
So friction is E dis, right? It's dissipating energy. So the little molecules along the surface are being disturbed and they're moving faster, and I suppose the temperature of these surfaces increases, and we're calling that energy dissipation, right? Molecular motion, essentially. You could say, think of it as the kinetic energy of the molecules. You guys good? If we can't, go ahead.
But if velocity is constant, then doesn't that mean there's friction?
Who said the velocity was going to be constant?
It says
Constant velocity.
constant velocity across the
Wow.
floor.
The book is pushed at a constant velocity.
Oh, okay.
The moment he lets go, though, it wouldn't have slowed down yet.
So the only way it's going to move with constant velocity while he's pushing is if there's friction to equal the force of his push. Yeah? You guys are good. Right on. So this is E dis. Beautiful question, Jules. How much do you want to lose to E dis? It's also going to be air, right? This book is traveling through air, and those air molecules are disturbed. So the air is going to, the temperature of the air in the room is going up a tiny bit. The temperature on the surfaces is going to go up a tiny bit. And notice that this molecular motion is storing energy. So this is energy transferred from our book to the molecules around. You guys good? Okay. And in the middle of this, these are the red part is energy that's transferring into or out of our system. We're losing 1 to E dis. So I'll say plus work minus E dis. Is everybody good here? And then I'll say equals that side of the equation. So how many blocks do I have in EK in the end, please? Okay.
What do you mean plus work?
Okay, more questions?
Why do you add work?
Okay, work doesn't always have to be added to our system, but this energy is going into our system because there's a force pushing in the same direction that the object is moving.
Yeah, I get that.
Okay? So that's how energy is added. You could have an object that's moving at you and you actually stop it. Are you putting energy into the object then?
Oh no.
So if like you catch a baseball, right? The baseball glove moves while you're catching it, right? The movement, the displacement is one way. Your force stopping the baseball is the other way. You're actually taking energy out of the baseball.
Yeah.
Does this make sense? Cool? Okay. Let's just make sure our equation makes sense. 0 plus 0 plus 0 plus 4 minus 1 is going to equal 0 plus 0 plus 3. Are we cool? I carefully picked a number between 0 and infinity. I like 4 because he's easy to draw. You should pick like 50 blocks and then distribute them. I think that would be fun. That'd be a good use of your time. You're like, should I do 49 or should I? No, I thought that was fun. So that was 2. That was number 2. So 2 is pretty easy, not too bad. Are we done with it yet?
No, the block has to stop. Yeah.
Does it stop yet?
No.
Darn. So the next part's pretty easy though. You can just copy this one, right? If only I had a smartboard and I could copy it. So I'm going to copy. Oh, that was great. That's what I wanted. Okay. Let me copy this junk, all of it. Smartboard fart. Okay. See if I can group them. Oh, come on, you can group together. I know you can. I know you can do this. There you go. It's like all in slow motion because the memory on the computer is so low. I took like 70 gigs of video files and took them off that computer and it's still going slow. I wonder what's going on. Maybe I need a new computer there. Okay, so is that everything? Did I copy it all correctly? I guess I need the 0 plus 0 plus 3. Does our system change? Just curious. Should our system change? No. So box, or book, or whatever it is. Everybody cool? Everybody good? How do we do this? What's going to be our end moment in time? Please. Okay, that's nice. Because I like that you chose when the book stops. It's very hard to draw that. So elastic, EG, EK, they're all gonna be what? So 0, 0, 0 equals what happened? We had 3. Where'd they go? All right.
Some more friction.
All right. So E this, and we lost 3. Everybody cool. So we got minus E dis. There's no energy going in through work.
Are you writing the system thing every time we have to do that? Or is it just like
We have
I think it's like how to write it out. Like really annoying to me. It's like,
Is the choice of your system going to be very important?
yeah.
Since you're an accountant and you're keeping track of the money in the bank, that's the energy in your system. You better know your bank.
Yeah, no, I mean it's always the book or something else.
No, you could have actually chosen the system to be the book and the hand, in which case there was already energy stored in the hand because they ate food. But it gets more complicated when you do that.
Then you have to have the 3 bins for each.
So your goal then is to keep this as simple as you can. Choose the simplest system you can do. I lost 3 here. So let's see if our equation works out. 3 minus 3 equals 0. 0 plus 0. And this is 0 plus 0. Are you guys cool? And this looks like it's totally cool. We're good. Okay, so now we're done with 2. So I'll just stop 2 real quick. And we'll make a video.